So basically we resume with my presentation now.
In a few minutes.
Perfect. This.
I guess there's a few points where maybe.
Okay, so welcome back from the lunch. Some of us did not survive. We will continue the perspective from the application community. Our next speaker is Andrea Ferretti from CNR, he's also a member of the MAX Center of Excellence. Andrea, thank you very much for taking time and connecting and doing the presentation. Please go ahead.
Yeah, thanks a lot, Franz, for the introduction and the invitation. So, during this presentation, I'm going to discuss some experience we had with benchmarking on electronic structured code within the MAX Center of Excellence. And here is a bit of the outline of my talk. So first, I introduce MAX just to give the context where the development on these electronic structured codes happens, and especially I'll spend a few words about some common workflows that are our target for the development, and then I'll briefly describe some of the daily activities we perform, especially concerning parallel performance and performance portability, where also I'll show some more benchmarks, and eventually I'll try to rationalize a bit about metrics and also using some more advanced metrics based on hardware counters in connection with code design. So here is one of the key aspects of exascale combined with or within materials modeling. Somehow we use electronic structure methods that are the base of quantum mechanical atomistic modeling of materials, perhaps eventually interface with multi-scale approaches, and these electronic structural methods are highly accurate and actually predictive, and they are computationally demanding, so somehow exascale is a real opportunity for this method, and this opportunity can be exploited in, let's say, in a number of ways. Here I'm listed 3 of them. First idea is that you can implement and improve modeling of your system, so you can actually include complexity within your simulation. It is pretty much the analogous of the 1 kilometer grid in the weather forecast simulation. So there you shrink the grid, here you enlarge the system, the description of the system you can have. Or you can exploit exascale to reach higher accuracy or to address more complicated properties. To be treated, I'll make an example, or eventually to combine these two with the high throughput string when you run thousands or tens of thousands of simulations to screen for some desired properties. Oops. Oh, yeah. So here is an example of complexity. This is a system studied experimentally. It's graphene on a transition metal on an iridium surface. And because of commensurability of the layers, graphene forms some array patterning. And at first, I don't know, 10 years ago, we were studying this, just neglecting the moire, but some physics and chemistry is actually connected to it. So indeed, with computational power, you can really perform a more accurate modeling. So this is an example of what I mean by including complexity in the simulations. And here is instead an example of a, let's say, a complex property that is color or reflectivity of a material. So bottom you have the colors of 3 metallic alloys, and top you have their simulation. So this means computing the electric matrix, the electric function, and actually get the reflectivity out of it. And you can really simulate the color of the metals, and so the results are quite astonishing in terms of quality. But the point is that you can do that. The property is complex to calculate, but you can do that is at reach, and you can also combine this with the high throughput screening. In this case, this was quite interesting. So there's an high throughput screening for some metals with desired metallic alloys with desired color. So somehow here you combine these two. And as you all know, somehow reaching the exascale means that you have to modify your tools, your software, your application in order to be able to exploit exascale class machines, because simply otherwise you won't be able really to run them. And within the domain of materials science, MAX, Materials Design at Exascale, Center of Excellence has been funded for the third phase now, so it's going to run for about 12 years, and is really focused on electronic structure codes. Here, the core codes are listed: Quantum Espresso, Celesta, Yambo, PGFT, Fleur, and AIDA is an orchestrator and workflow manager. Of course, in order to work with these codes, you need to have the right partnership, so somehow you need to involve the scientific communities developing the codes. You need to have HPC expertise, so to have HPC centers involved, and also to have hardware vendors and partners, since we are also supposed to directly interact with the hardware in, let's say, co-design activities. And in terms of activities, what is relevant for today's discussion is that we have to perform parallel optimization and performance portability for these codes, and importantly, so all MAX codes are really release production ready for GPUs, mostly NVIDIA GPUs, but we know that we also need to target the different brands, AMD, Intel, and so on and so forth. We have co-design activities, and also we have activities about energy efficiency of the codes, and all of these require benchmarking of the codes. And needless to say to this audience, so targeting exascale means really to the largest extent that we need to deal with accelerated systems. Here is just an example of Frontier, top 500 machine, but also European machines. They are all accelerated. So this is really within the core business of what we do, and it's relevant in terms of benchmarking, since somehow we need to know the target we have to achieve in order to understand how to use or what kind of metrics to put in place. So concerning codes, so parallel optimization and performance portability, just with a simple calculation, somehow if our goal, our final goal is to turn MAX flagship codes into exascale enabled application, that means that we need to have runs that occupy or take of the order of tens of thousands of GPUs. So somehow having large MPI scaling with the order of 10,000 or tens of thousands of tasks combined with GPU awareness. And this also poses a number of issues concerning maintainability and sustainability of the code. This is going to be the subject of tomorrow's discussion, but let me just briefly mention that here we have put in place a number of strategies concerning the use of standards for programming models, optimize vendor libraries, but also to refurbish the sources of the codes in a way to not disrupt them. And this is another key aspect. So the codes we are working with are community codes, and it's important that we keep the community engaged. So it's not enough just to take the code and revert them to be able to exploit at best a given architecture, but losing the communities, because the value of the code is really in the communities. In order to do so, somehow we have over the years developed a little and in-house version of a performance portability library that is called Device Sleep, especially within the communities of Quantum Espresso and Yambo. We've been using this in a way to, let's say, hide to a lower level the complexity of the multi-brand, multi-software stack details of GPUs. Okay, this slide here is an example from a few years ago about just CPU only scalability on KNL, reaching 10,000 plus. This is not really exascale any longer. The problem is to do this together with the GPU. So we started early on to work on GPU portability, and here are some benchmarks where we just plot time to solution versus number of nodes, so in a strong scalability fashion. We run this on systems that are, let's say, scientifically relevant and typically were used for scientific production a few years earlier. This is still within our interest. This is artifacted TiO2 bulk for photocatalytic applications, and with this we've been comparing runs on state-of-the-art CPU at the time, and then GPU-enabled accelerated machines like Power 9 plus Volta and NVIDIA DGX nodes. And here we were comparing across different, so first of all looking at the parallel performance, but then also comparing across different machines, keeping, for instance, the number of nodes constant, looking, so for instance, we had a gain of times 14 in going from one Skylake node to one Marconi 100 node, and then another 1.4 factor going to a DGX node properly scaled. That makes sense. Here we have twice as many GPUs. And that was the case of a few GPU nodes here. Instead, later on, we went to Jewel's booster, and this is a large run for the time that was taking up to 40% of the machine, that I think was the maximum available because of the queuing policies. And if you notice, the system has changed, and this is another point, is we try to keep the benchmarking cases as stable as possible, but as we increase the size of the machine, then the use cases that are relevant or were relevant for the previous runs may not be relevant any longer. So we need to update our set of use cases, and this is an activity that we have been doing. By the way, all the benchmark cases and results are uploaded on this public website, so one can just also take a look and add all the references there. And so here we were also quite happy at the time by the parallel efficiency, and later on with the same system we were able to run on basically 90% of the newly deployed Leonardo machine, about 12,000 GPUs in a single run. This is a special case within Max, since this is not the standard density function theory. This is many-body perturbation theory, GW method. This is a heavier workflow with respect to standard. It is still here. We are getting close to our target, so some of this could be seen as a exascale or a pre-exascale calculation in a sense. Okay, also this is another example from Quantum Espresso that have been running on both Leonardo and Lumi. In particular here, they've been benchmarking on Lumi the porting of Quantum Espresso based on OpenMP, and also they've been improving, I would say, extending the OpenACC based porting at the expenses of the CUDA Fortran based porting for NVIDIA machines. And here, kernel by kernel and feature by feature, basically you can see that you improve on the acceleration you get out of Lumi. Indeed, we were very happy to see that quantum espresso Lumi were started to perform in a sense as compared, in this case, to Marconi 100, because not all kernels were ported. Now there are more newer data on this. But this slide, so the take-home message of this slide is that, again, concerning metrics, zeroth order metric is just that we need to be able to run. And this is not trivial at all. And I think Lumi is a clear case for that, because it's a super advanced hardware that also require as its own software stack, and so requires significant work on the side of the application to support. And so concerning our KPIs, somehow being able to run on Lumi is one of the actions to achieve. So this is, in a sense, a metric in itself. Okay, and still part of the context, all of this is done while new features are added to the code. This is a new implementation of GW with advanced features, or new algorithms are included. This is an algorithm targeting 2D materials, which has quite a high at the moment in material science, so are quite relevant, or even advanced logics for workflows are developed. And all of these somehow have to do with benchmarking, since they provide new use cases for benchmarking. So this algorithm here, by the way, is what has been tested on Leonardo, so the random 12,000 card that just shown to you. So this is somehow the context, and somehow what we produce as benchmarking on a daily basis. Let's look a bit more closer, and let's try to rationalize a bit. And here is, let's say, out of the same data set that you produce to plot time to solution versus number of nodes, you could also just produce plots in this form here, that is cost, so times number of nodes versus time, and same data, okay, but somehow here, if your cost stays constant, somehow you have perfect scaling. So you simply use more nodes and you take less time, but the actual cost is exactly the same. The advantage here is that you start feeling that you are worsening your situation where this curve just go up, since your cost is improving, and some of this is relevant, for instance, to users. The users really care about how much of their budget is consumed on a run, and from our point of view, we can even compare architectures here on a different basis. So if we multiply this cost here by the average power consumption, this is really a rough estimate, but we could get a cost in energy. So energy to solution is a very rough estimate, I know, but somehow it doesn't require any extra piece of information other than the time to solution we have been using. And somehow this graph tells us that, yeah, we can more or less put all of this together, and here is how KNL CPU only compares with GPU accelerated machines in terms of energy. So we had an improved scaling because we were using less NPIs, and also we know that the hardware takes less power. So overall, we had a significant improvement in terms of energy. Of course, then we can go to really hardware counters and advanced metrics. So thanks to Fabio Finito for providing these slides here. This activity comes from Max2 operations, and for each codes, basically we were looking at execution time, instruction per cycle, vectorization, ration, time spent in the app versus time spent in MPI, clocks, energy efficiency. So these are more advanced metrics that have been measured and then compared. So now here we are really bridging towards a more co-design oriented kind of activities. And with these metrics, we were also able to make a roofline model study or positioning of Max codes for different versions, also learning something about our own codes in terms of CPU bound versus memory bound kind of analysis. So all of this is possible, has been done within a selected set of cases. And last but not least, let me just mention how, so that our, within Max3, our benchmarking activities are organized around the JUBE benchmarking environment that has been, is under adoption within our activities. Okay, here my conclusions also for the sake of discussion concerning benchmarking. So first of all, we have to identify test cases that we need to be reliable and meaningful from the point of view of the science, and these are regularly updated, especially because getting larger machines means that we get different workflows that become more or less relevant. Then the data are all available here. Everything is done within, or is going to be done within JUBE. Mostly have shown time to solution kind of metrics, but also cost versus time seems an interesting alternative. Of course, we can also take advantage of hardware counters and access different metrics, especially for co-design purposes. And let's say there's a lot of emphasis on energy to solution kind of matrices. We have a dedicated task on this, so more about this energy to solution and optimization of the energy to solution is to come. And we've been using most of this to compare the parallel performance and the performance portability across different architecture. In terms of difficulties, let me mention that the non-maturity and inhomogeneity of the software stack is a strong limitation, so it's difficult from the point of view of software developers to use very advanced metrics when there is, let's say, dishomogeneity in the software stack and so on and so forth. And if life is difficult for simple workflows, say, let's say, single run of a single code, then life becomes even more complicated when going to workflows. So there, finding, figuring out what are the relevant metrics or set of metrics is even more critical. With this, let me just thank you for the attention, and also let me thank in particular Nicola Spallanzani and Fabio Finito, who's basically attending there, also for help and providing the information. Thanks to you all.
Thank you, Andrea. Any question for Andrea in the room? So,
maybe just not really a question, maybe a comment. This is the second time I see today that people were trying to use JUBE up to 300 something nodes. This is Damien from JAC, by the way. So if anybody really wants to use more nodes, please just let us know. We are more than happy to accommodate these kind of things. So sorry for that.
Thanks. Good to know. Good to know.
and yeah, maybe more a comment on my side. So seeing the multiple metrics you mentioned, Andrea, I would say that maybe one metric is more important. Well, the priority of one metric depends on the use case. Maybe sometimes the time to solution is more important. In another context, maybe it's more energy to solution. Can you detail maybe a little bit more about energy to solution? Up to you, what's missing, maybe?
So energy to solution, we had some. I'm not sure I got the question 100%, but the energy to solution, we did some measurements during the previous phase of MAX, and now we are planning to do even more. There's a task in charge of IT4I within MAX that is really going to perform perform two actions. Somehow one is optimization within, of measurement within mini apps for the sake of co-design, and another one that is really full-scale optimization of the energy consumption by first performing measurements and then putting in place some tuning of the hardware.
And also for energy to solution, do you explore, for example, mixed precision, things like that?
Sorry, could you say it again?
Do you explore mixed numerical precision, this kind of thing?
Yeah. We did some mixed precision experiments. I have to say, mostly single, double. We didn't go much below, so we didn't try extensively with half precision. That is surely, I mean, the experience was very positive. So somehow we came with codes that were all double precision, and you just realized that there are many parts that could just be run single precision out of the box. Then we had to take care of numerical stability a bit, but somehow that was possible without restoring the complete double precision. So it was just a matter of understanding which parts were really critical, which accumulators were really critical to be running double precision, and then everything else worked very smoothly. Experience with lower precision is still a bit limited, but surely interesting.
Thank you. Any other question or comment for Andrea? No. Then you're free, Andrea. Thank you very much.
Thank you very much.
From CA, astrophysicist and research director at CA.
All right. Hello, everybody. This may be the talk you didn't want to listen to, but that when you are going to leave the room, you say, I'm happy I listened to this talk. And I'm going to tell you why. Because what I'm going to speak about is going to tell you that actually what the research we are doing at CEA matters not only for Earth, but also for the technology. And it's going to be much clearer in a few minutes. So, as Franz told us, we are trying, this is work that has started also by colleagues working at the University of Colorado. We are trying to understand the the sun. And I want to emphasize how numerical simulation, but more importantly, their validation, can help us progress in our understanding of the sun. So here what you see is a cartoon image, the sun, the earth, and there are a lot of things going on between the two. And that's what I'm going to emphasize. That's part of a European Research Council project called Whole Sun, where we try to understand the sun as a whole. So just to start in a context, so maybe not everybody have seen, this is a UV image of the sun for 2 months, and you see there are bright active regions and dark regions, and that it's controlled by the magnetism of the sun and the magnetic field lines that you are seeing. And of course, the sun is a big sphere of plasma, hot plasma, that is conducting, generate magnetism, and there is a lot of turbulence. So we have to deal with a very complex plasma phenomena that we need to understand with a lot of different regimes. So I'm going to show you a few, at least if the talk is not interesting, you will have seen nice images, okay, of our star. So here, this is the enhancement of the coronal part. So you can see that we have a lot of strays leaving the sun, and this is, and you see some magnetic cloud leaving. So we are living around an active star, and as you know, there are a big international program which is called Living with a Star, and that's what we are, because not everybody realizes that the Earth actually bathes into the sun's atmosphere. So if the sun has a tremor, an eruption, but of course the Earth will most likely feel this tremor and activity. So just want to show you this few movies. It's not going to be very long, but so again, magnetic clouds, you are zooming in into the sun. These are various movies done with various satellites, some from NASA, some from ESA, some from JAXA in Japan. So it's an international effort. So here you have an eruption. This in red is X-ray, in blue is hard X-ray, in green UV images, in red and blue white light, and you see you have starting to have a part of the answer what it may matter for you. All this snowflake effect, noisy effect that you see on the detectors of the satellite are actually high energy particles thrown at us by the sun. So you imagine that if that can do that to a CCD, that can easily do that to any microchips that we have, either on-board satellites or, of course, on ground. And that's one of the points. So just to give you a little bit more information, this is a sight of the sun view from above the solar system. The Earth is around there, and you see there is a spiral that we call the Parker spiral. And this is, the Earth is embedded into this magnetic spiral that extends over millions, billions of kilometers and wrapped around several times until you reach what we call the heliopause, where recently the 2 Voyager missions sent by NASA in mid-70s have went through. Okay, so we live in a very turbulent and complex. And on top of that, not only there is this continuous activity of the sun, with sometimes transient storms and a continuous wind, but the sun has a solar cycle. And this solar cycle goes back, at least in historical record, to the mid-18th century. So here we have started the 25th sunspot cycle, and we are predicting a slightly more active sun than the previous cycle that was quite weak. And so we are certainly restarting. So we are in 2023, the minimum was in December 2019, so we have been more than 3 years in, almost 4 years in the solar cycle, so this means more activity. So just to show you, this is a movie we have done with the current code we have been using. This code was a joint effort between my colleagues in the US and here at CEA, and this has been running fine for 2 decades on CPUs using modern MPI and modern Fortran. but we are starting to be limited. So here I did a kind of flyby like Luke Skywalker on his X-wing over the Death Star, but this is a numerical simulation of what we can currently do among the best. There are also colleagues in Japan who are doing excellent simulation of the very similar. And so we can also try to represent the solar wind. We can do UV emission of the simulation. Of course, they are not as resolved as the real sun. We are not quite there. But we are able to reproduce a lot of features, but we have to do that with a different code. And just to finish, what we have learned from the sun and star planet interaction, we can extend to stars and exoplanets. So here you have a planet that is much closer to a star than Mercury is to the sun. And sometimes the planets, and when we are in the universe and we are interested by exoplanets and questions like habitability, this is very important to be able to understand how a star actually generates and controls its heliosphere, or what we call astrosphere when it's constant stars. So enough with nice movies and a context of astrophysics. So why do we do that? But there is not only an interesting question from an astrophysical point of view, which is to understand the sun. There is also a very pragmatic aspect that we call space weather. We live in a technological society, and the Earth, as I say, bathes in the sun's atmosphere. And when this atmosphere is turbulent, magnetic, and evolves in time with the cycles, solar 11-year cycle, making it even more so. So the maximum is expected in 2025. So you are going to expect more and more aurora borealis and such things. So the sun's activity can have an impact on nearby space, so on satellites and astronauts. So GPS, for example, can be impacted by the sun. It has an impact on atmosphere, so you can have problems with communication, with flights. There are often flights. Well, before the Ukrainian war, the invasion by Russia of Ukraine, we were flying a lot when we were going to Japan. We were flying a lot over Siberia. Now, when we go to Japan, we tend to take the soft road. But when you're in the US, you don't have to do that. But in Europe, that was what we were doing. So I took a Geiger counter in the plane to see, and indeed you have a dangerous radiation background. I can show you the image. Okay. So when you fly at high latitude, high altitude, and close to the North Pole of the Earth, you can be impacted by a lot of radiation. You don't want to stay there too long. And of course, if there is a storm coming, we have to ask the pilot to change his trajectory to get more protection from the Earth magnetosphere. And of course, we can have impact on the ground. And here, that starts impacting us directly, because you can have what we call geomagnetically induced currents, and these jigs are actually impacting electric grid, pipelines, aqueducts, and networks. And of course, we have a lot of particles, and these big machines that we are building, these exascale and beyond exascale machines, are actually big gamma ray detectors. They detect a lot. So I don't know, we have people in charge of computing centers here. I don't know how often you have high energy particles impacting your machines, but that can trigger errors and can lead to problems. So there were a study that if an event like the Carrington event in 1859 was burned, a lot of telegraph and stuff like that will occur now, it will cost about $2 trillion to the community. We will have a total collapse. So I don't want to be a catastrophist, but I just want to say that there is a lot of impact. So in order to prevent and mitigate this impact of our active sun onto our technological society, we need a better model of the sun and how it controls the heliosphere. So we have currently at least 6 or 7 satellites going around in the solar systems or close to the Earth to monitor this phenomena. And there are 2, one from NASA and OAA that will be sent, and one from ESA that are going to be sent in the year to come, to be put at certain location to improve our ability to forecast. So we have an ability, we need to be able to forecast. So for that, if we want to be high resolution, to have all the physics, and to couple the inside and the outside of the sun, we need exascale computers. We need a new code, because the codes we have currently are either very localized boxes or global models that doesn't go all the way to the surface, even though they give nice movies, and we have learned a lot from that. And we need an international benchmark validation. So that's where the benchmark comes. So I'm going to just show you a few things. I'm not expecting you to look at the numbers. So back 15 years ago, we developed a solar mean field dynamo benchmark. So where a bunch of people, US, France, Europe, and also India, I think. And we were developing a model that was able to reproduce the 11-year cycle. So we have simple models that can be run extensively, and we have done a lot of tests. So here I just underline few numbers, forget about the things, but with this benchmark we were able to test two things: the accuracy of the solutions and how fast you were getting to it, and the agreement of the solution. And from the study here, we were able to find about 1% of accuracy. So this was satisfactory and interesting. And we also looked at a more involved simulation, and we did some tests of convergence with resolution. And as we were increasing the resolution, we were finding that the convergence to this 1% was working more and more. But of course, this is not perfect. This is not the same numerical techniques, not the same code, not the same computer, etc., etc. So we expect to have some departure from a perfect agreement, but we found that was very nice to be able to capture the frequency of the solution. That was an easy benchmark to do, but that was useful. So I spare you the details of the equation, but we went then to make, with a different community, a more involved benchmark, which was on 3D convection in stars and planets, like Jupiter, for example, and 3D convective dynamos, like inside the Earth core. And so we agreed on that benchmark. We had to agree on the background state. We had to agree on the set of equations we were solving. We had a couple PDEs, a partial differential equation that were with 8 primary variables that were all 3D. And so we had to agree. So I spare you the details of this, but just to tell you that we had to agree on a lot of parameters of the solution: density stratification, the thickness of the shell, various turbulent and fluid numbers like the Reynolds, Prandtl, Rayleigh. I spare you the zoo of fluid numbers, but we had to agree on that. And we found that the definition that we had as scientists were not the same, and that was explaining some of the discrepancy we were finding. So yeah, it's a simple solution on a sphere, and we have a bunch of numbers. I spare you, but again, agreement within 1%. But this was, we were doing various validation tests. We were testing integral values, so global energies, and we were also looking at point-wise value. For example, what was the value of the velocity at a given position inside the simulation. We were also looking at other fields like temperature or density, and we had to record exact value at a given location. This was possible because the solution we had, as you can see, is very wavy-like, very regular, and so that was not too difficult to be able to be very specific on validating the output of the result, and we did that pretty well. So then we wanted to go to a more turbulent state and to add magnetism, and so we went to a highly stratified system that required a long time of integration because you need to relax the thermal structure of the simulation. We also wanted to push the turbulent state, and this implies long temporal averages to compare outputs. So that was a bit different, less systematic and perhaps less accurate in terms of comparing the codes, but on the overall, we were sometimes in a better agreement than 1%. So then I come down to discussing the new code. So these were former benchmarks that we did in our community in order to try to start agreeing on the behavior of rotating, convective, and magnetized sphere of plasma like we have in planets and stars. But we were limited in the regime, parameter regime that the simulation were able to achieve because sometimes in physical body, like we are interested in the universe, you can have a large range of space and temporal, spatial and temporal scales, as well as a lot of multiphysics. So we are developing at CEA with colleagues elsewhere in France what we call Diablo. Diablo is a framework which is based on adaptative mesh refinement framework, which try to improve our ability to compute high precision turbulent fluid and plasma without putting all the effort at every grid sense. This is based on two aspects, a parallel AMR library interface, one that we developed or one that was already there, Pablo, and also a much known COCOS library developed by DOE and others, and where we are able to have easy platform performance transport. So, of course, the previous code I was showing you were CPU-based code, and this one can do, thanks to COCOS, either GPUs, CPUs, or even ARMs. Right now, we are working on trying to use FX64 processor and stuff like that. So just to give you some performance tests that we have done on scalability, this is a set-off blast, so it's a kind of a big detonation in 3D with a 512 cube. The big simulation I showed at the beginning of the sun was closer to a 4,000 cube simulation. But, so we have run on Cascade Lake Intel CPUs, 40 cores per node, 4 MPI process per node, and we have reached 2048, so about 20,480 GPU cores. And at one point, the simulation started to have issues with the output, but otherwise the technology seems to be working fine. Because AMR code, adaptative mesh refinement code, are not that new in astrophysics. To do cosmology, we needed to have AMR code already. It's to apply them to plasma physics that is a bit more new. But we're having a problem with the octree, the fact that when you have cell-based AMR, you have difficulty to actually perform well and scale up to 5 or 10,000 core. So we needed to change our way of doing the AMR, and we went from cell-based to what we call block-based. And we have a big block now that we can put on the GPU memory, and that avoids to have I/O between CPU and GPU a lot, and you can perform much better by filling up the memory of the GPU. So just to show you that this code works and does nice things, this is will come back here. So this is convection at various degree of turbulence, and it starts resembling when you increase the turbulence degree and you lower the viscosity in the model, you are starting to look more like convection at the surface of the sun. So these were benchmarks that were inspired by a paper published in 1991 in Astrophysical Journal. So it's always difficult when you take all papers like that were not designed to be benchmark papers, because they usually don't give all the small details that you need to do a very precise benchmark comparison. But we were able to reproduce most of the results, and we know them a little bit. I know Fausto Cataneo and Nick Blumel who are part of this paper, so that was a bit easier for me to discuss with them. So we, to reproduce these results, we had 9 code involves, some from Chiba University, R2D2 that I'm sure our Japanese colleague knows, some from CEA, some from Max Planck, some from UK, etc., etc. So one from University of Colorado and called Daedalus. So various methods, and we were about reproducing the same result. Of course, there is more than a 1% difference, so we are still working on it to understand why there is not such. There is good agreement, but not as good as before. So to show you what the convection with AMR is giving us, this is just with 3 levels. So here you see that the mesh is trying to follow the downflow lanes, And here, sometimes we are over resolving, and that's certainly due to our criteria. So with AMR, there is also, in terms of efficiency, time to solution, or energy to solution, you need to be sure also of your criteria that you use. So we also did other tests. Here we have 4 codes, 2 that are fixed grid, Bifrost and Mancha, and 2 that have AMR, Dispatch and Diablo. And we are trying to get what we call the hydrostatic equilibrium. So at the beginning, you need to, in a star, you need to equilibrate your density, your pressure and your gravity. And it turns out that finite volume code have a difficulty to maintain the hydrostatic equilibrium, because you have a way of, when you do what we call the Riemann solve, you tend to have a discrepancy between left and right, and so sometimes this is not very good for maintaining the hydrostatic equilibrium, which is a very key feature of the planetary atmosphere and also of most stars that are not in a very active phase of their life. So here I want to show you a little bit more something very interesting. Here you have 3 codes. This is the Diablo code with AMR, this is Dispatch, the other code with AMR, and this is Bifrost, which is one of the standards in the community. And we see that by having the AMR, we are able to reproduce similar results than what they have in Bifrost, but we are getting much more advanced structure and much more secondary instabilities in the downflow lanes of the convection. And convection is just macroscopic motion transporting heat inside the star. So we find that it works better. And when we compare with the DEKIST solar telescope from the US, that is in Hawaii, we find a better agreement with the AMR code. So we see that already we are able to reach a level of realism that is much closer to what the sun is telling us. We also need to test MHD solvers, and so right now we are still working on it. So you can see that this is a very interesting test. So I want to say that there is not only benchmark, also unitary tests are very important. So in Diablo we have a whole suite of unitary tests. And so at the beginning, the very basic way of doing MHD, which is magnetohydrodynamics, works so-so, but you can see that when you try to implement other methods, it can be even worse. These are very tough problems. You have to advect diagonally a vortex, and so you can see some spurious effects when you let the simulation go and go and go. So we are still working on trying to validate. So in some tests, like Orzactang or other plasma tests, it works well, but for this very difficult test, where you need to be close to various Mach numbers, you can have some issues. So still, we have done some MHD simulation with the AMR code, and here we are lucky because the magnetic field tends to converge towards the downflow lanes. So if you have a criteria for the refinement, which is based on the downflow lanes, then you can have the magnetic field as well. But it's not always the case, so there is a lot of work to make it work better, and we will certainly do a magnetized convection benchmark soon. So, and just to finish, right now, of course, you are going to say, Mr. Brown, the sun is not a cube, it's a sphere. So how do you go from your nice AMR cube to the sphere? So there are some works in progress. There are some mathematicians that have shown that there is some way to go from a unitary AMR Cartesian cube into a spherical grid. So here you have the isomorphism that lets you go from one to the other. And we just had the master student finishing, who will start his PhD with us on Monday, who has done the first implementation in Diablo of the sphere. And so we are starting to be able to do Kelvin and Mohs instability in a ring, where we are able to, and this is solved in a cube, and we are able to put it on a sphere and to take that into account. So we have also relay Taylor instability, so we are getting ready to be able to deal with possibly the sun. So to conclude, I hope I convince you that understanding the sun and its heliosphere is key for our modern society. Solar activity can have major impacts on Earth, even on supercomputers. solar energetic particles or GICs can damage network and processors. Developing exascale and beyond ready solar plasma code is critical to describe our star. We need higher degree of turbulence. We have a large range of temporal and spatial scales. We have a multi-physics and multi-regime. Our Mach number changes. We need radiative transfer. We have high energy particles, so we don't only have fluids, but we will also have single particles to advect and to process. So we need to have unitary test and international benchmark in order to achieve this ambitious goal and to try to understand our star. Thank you very much.
Science. In order to impact the societal challenges that you highlighted with solar winds and other impacts on our infrastructure, using this code, how quickly would you need to be able to produce answers for the code?
Oh, that's a very good point. So we are currently, both in the US and in Europe and also in Japan, there is now a procedure to take this most advanced code and to make a pre-operational version in order to be able to run them on a daily basis. It's even more than a daily basis. Because to give you an idea, a magnetic cloud takes several days to come for the standard one, but the fastest one can take half a day. And the energetic particles that are very impactful for satellites, but also our network and supercomputers, they take 15 minutes.
So would you want to do an ensemble of those runs?
Yes.
Just to have an early warning system? So what's your estimate for your time to completion for this early warning system to be useful?
So I'm not sure that the community right now is expecting to be able to have a warning for the solar energetic particles because they are almost at the speed of light. So if you don't have a pre-modeling of the structure, you cannot really, when it flares and goes, it's almost impossible to run a model.
What is it, 8 minutes, right?
Yeah, yes, 15 because it don't exactly go at the speed of light, but yes, 15 minutes. That's too short. But the magnetic clouds and the eruption that we can model. So that's why we are developing satellites that will look slightly ahead of the Earth-Sun line. And because of this spiral that you have seen, the active regions that flares are the ones that are on the, if you look at the sun, the ones that are on the right-hand side. The ones that are on the left-hand side of the sun, if they flare, they go in a direction that doesn't impact the Earth. Okay? So we know that we have to be able to model the structure as they pass in front of the solar disk, and then of course it's complex, so you either want to model everything or just the active region. So to a short answer, you need to be able to run below 12 hours if you want to be able to do something that is useful for the community.
Is anyone trying to reformulate the problem as inference?
Yes, I mean, an ensemble are being done right now. They are at NOAA in Boulder, in Leuven and Bruxelles in Europe, with input from all European countries, and in Japan, there are 3 operational centers that are running models of the sun and heliosphere, but they are of course under-resolved models to be able to go fast, you know. So it's a bit like for people who are doing weather forecasting. You have the ab initio models that tell you what is a water cycle, and then you have people who are doing weather forecasting who have a recipe for the water cycle. You know, we are doing a bit of the same. We are trailing our colleagues who are doing weather forecasting, but we are trying to catch up because we are learning from their experience.
And okay, a lot of other questions.
This is a brief one. It's just another angle on the previous question. In the area of simulation that you are doing, how much potential is there for acceleration of parts of your algorithm using AI methods?
So that's a question we are really asking ourselves. I know that now there are physically informed AI methods. Up to now, with the fact that we needed to conserve the divergence of B, the fact that we needed to have some, invariant in the system, we were very, skeptical to use AI that can give you, for subgrid scale models, typically, we need to have subgrid scale modeling, you could have issues with basic physical laws of conservation. But now I heard that there are new ways of doing machine learning, deep learning algorithm with physically informed, where you impose a constraint of, for example, dB equals 0. And if we can do that, we are going to look into that. The other option that I'm starting to consider, I'm not sure if it's realistic or not, that given that we have a space parameter of perhaps 6 or 7 or 8 parameters, it's a huge 8D parameter space to cover with numerical simulations that are very costly. So the question is, can you compute how many of these 3D high resolution simulations we will need to be able to pave the parameter space and then take AI to actually do the interpolation for you and not run the simulation. That will be efficient from an ecology, energy point of view, and maybe for the time. But what I don't know is how many of these 3D advanced simulation I need to be able to do the teaching and of the AI. And that's where it's difficult. So if people have experience with that, I'm very happy to discuss it. We are thinking about it. We are not sure it's practically doable, but at least we are thinking about that, because each time you want to change a parameter by a factor of 10%, is this really worth redoing everything? I don't think so. You know?
So, in your mesh, it seems to be mostly refined. Is the AMR buying you enough to justify the added how bookkeeping and complication that it adds to the system?
You're completely right. The one that I have shown you were not optimized. They are, we are developing the code. They work. We were happy to see we were tracking well the downflow lanes, but I definitely agree with you. We are over-resolved, and so we need to be able to start with a coarser grid and to be able to refine only where we need. So this is part of the work we are going to do with my postdoc and students, is to really learn at developing these refinement criteria that are non-trivial when you have a multi-physics problem. But yes, I agree with you, you need to find this right balance between increasing the simulation by a factor of 2 for the basic grid and not bother, or having an optimized AMR that avoid having this resolution. And also the time stepping can be hierarchical, that give you also value sometimes.
Right, and also when you start to include radiative transfer in there, that starts to dominate the computing time completely, and that usually wants to be uniform grid rather than adaptive meshing.
Yes,
So
that's why we think that the idea of the unitary code, the cube, maybe because radiative transfer on the sphere has not really been, AMR sphere has never been done, but radiative transfer through AMR cube has been done. So we are thinking that maybe we can use some of these techniques and then use our isomorphism to go to the sphere. But usually people say that it depends the level of radiative transfer you want to do. I think for us, since we want to cover the solar cycle, we don't want to be too detailed, just one ray, perhaps a very simple, radiative transfer, better than Eddington diffusion approximation. And then for local runs, for 1 or 2 hours of run, rather than a decade, then maybe have a more advanced where it will not matter too much because we will just do a short run. You see what I mean? So we have to have a strategy there. We cannot run with everything at 100% for the length of a solar cycle. We need a machine beyond exascale to do that, I think.
One more question. Then that will be mine. Sorry. 2 more questions.
Hello, can you give us a little bit more details about the portability of the code, thanks to Cocos?
But yeah, it's really portable. As far as I can tell you, we have been able to run on many different structures. Right now, we are working on the A64FX. We are running, of course, on V100, A100. We haven't had access yet to the H100, but that's, I just have a benchmark ready to send to our colleague to test on the H100 because they are much more costly than the A100, and I want to know if there is a gain as much in speed that there is in money you have to pay to get it. And they are AI driven rather than HPC driven, so we are not completely sure. But if people have experience with the H100, I'm happy to discuss that at the coffee break. So what I can tell you is that Cocos works very well for us and has given us an edge in terms of portability. So we are happy to be able to we hope that DOE will maintain it for a long time.
Just a quick question from me. In your presentation, I really appreciate when you presented all the metrics for the benchmarking, really all the process. How hard it was to gather everyone around the table and define and agree, and how long it takes?
I mean, for everybody who has done a benchmark, I'm not just speaking of scalability, but really of a physical problem. It's a nightmare because sometimes, sometimes you think you have agreed and you did not. You don't have the same definition of something. Sometimes there are factor of 2, which are very large, but sometimes more subtle differences. It takes a lot of effort, and I can tell you that in my case, in one of the benchmarks, this helped me solve a problem I had in the code. So sometimes it really helps you because you're saying, why I'm able to do this case, I'm able to do that case, but that middle case I'm not able to reproduce. And that on that middle case, we were missing something in the code that we were able to implement back, and then we were able to recover. So it's very useful. And usually, when you don't reproduce the result of others, it means that you have a bug.
And this is a living work, like you continue to gather around this definition?
For the benchmark, no, the one we published in 2008, I think is now the world standard. So people who want to develop code for that, they use that benchmark. The one for 2011 is also world standard now. So people use that benchmark and they don't develop a new one, they just try to reproduce it. So the new benchmark we are developing is really one for compressible convection that has not really been done as thoroughly as we needed. So that's why we are working on it.
Thank you very much. Any other question? We are late anyway, so a bit more, a bit less, you know. Okay. One more question? No? Okay. Thank you very much, Sasha. Different point of view, and I think this discussion is very interesting. So our first speaker is Jack Wells from NVIDIA, and Jack is Science and Program Manager at NVIDIA.
Okay. Yes, I'm Jack Wells. Very motivated to get through this talk and get some conversation started. It's a collection of ideas motivated by the organizers that I hope indeed will be conversation starters. So indeed, there's a challenge that was just articulated. Scientifically faithful and sustainable benchmarks is a hard problem. That's why we're talking about it here in 2023. It's difficult. But they should be developed in a way that's faithful to the modern scientific applications and workflows that they aspire to support. And as has already been made a point today, there's an opportunity for increased and more open development of such benchmarks. And I'll try to repeat this point as I go forward. The goals would be to track the science and engineering capability progress. We use benchmarks to track our progress and capabilities. To be realistic challenges for technology and system R&D is to influence industry and what industry produces. This has already been talked about today. And to provide high quality marketing and communications to stakeholders and society, which we haven't talked about so much today, but it's an important part of benchmarking. Sustaining the vitality and the relevance of benchmarks over time is difficult. This increased open community-based collaboration that we're envisioning would be helpful. Having the application developers remain engaged, remain connected to the benchmark curation is also an advantage, so that they're not disconnected from the originators. It's disconnected from its home. And an ongoing discussion of science benchmarks outside of the business motion of supercomputing should improve the quality. That is, by the time there's a procurement afoot, it's too late to think deeply about benchmarks because now you're executing on your benchmarks. So we need to be engaged in this process in an ongoing way that's somehow extracted from the closed nature of procurement activity. From an industry perspective, at least from NVIDIA's perspective, these are at least 3 use cases for benchmark. There may be more. You may think of some that I missed. The key thing, though, that influences the quality of all that follows is to identify key applications that you care about. And this could be an independent code, or looking more to the future, this could be a workflow. And then identify benchmarks that represent important workloads or use cases in that application or workflow. And then once you have that, you can use it to try to improve the software. You want just the software to run faster on the platforms you have. So you would assess the software engineering opportunity, and maybe also assess the opportunity to improve the system software tool chain, the compilers and things like this. This is one use case for benchmarks. Another is to inform a future product roadmap. That is, applications that can be included in the design process for technology providers like NVIDIA or others, and this can then influence future product design. Right? And then the third I would call out is the go-to-market motion or the procurement motion. This is another part of the process. And here you're doing performance studies, you're maybe producing rankings of benchmarks, and otherwise doing performance projections. We've discussed many of these things so far. So I want to highlight something that's obvious, but we should all recognize it. There's tremendous influence through communicating benchmark lists. And maybe in the HPC community, the most prominent case of this will be the top 500 benchmark, right? And so a well-curated and communicated list of benchmarks has proven to be very influential. In fact, some would say there's only one benchmark list of supercomputing because at some level, in certain levels of stakeholders, they're not aware of any others because none others have been communicated as effectively as the top 500 has been communicated. And just, if you want to have some perspective on the influence of the top 500 list, I just invite you to listen to Jack Dongarra's lecture for the AEM Turing Award at last supercomputing conference. Right? He really does a good job of making clear the influence of making lists. And so if one aspires to have influence on that level, one has to pay attention to the principles of marketing and communication. That has a tremendous amount to do with the success of the top 500. So, there's no two ways about it. Marketing and communication is part of this game. So there would be, for benchmarking activities, there would be a variety of governance models that could be used to increase sustainability, right? Top 500 has a business model behind it, right? The top 500 is the property of a company. It's a small company, right? This is the trademark statement on the website. You can find it yourself, right? It's privately held, and there's a whole marketing infrastructure behind it that largely explains its 30-year lifetime, right? There's other options for the governance model. MLPerf has an open governance model. You can read all about it on the ML Commons website. You can participate, you can change it. One has been sustainable. Again, it's a property of a small company in Europe, right? The other is an open community activity, right? And so when you start thinking about these lists, you have to think about, well, what do you want to be a part of? What do you think is sustainable and right for your community? Okay, energy efficiency. We know that energy efficiency has grown to be a primary consideration. Denard scaling ended in 2005. We're approaching the end of Moore's Law. All energy consumption is growing, and it's depending on the use of the mix of electricity to generate, the use of fuel to generate electricity, then it gets into a lot of other things well outside of our domain of high-performance computing and science, but we are interested in the energy efficiency of this. And accelerated computing has been driving these more energy efficient data centers. Now, there's certainly a big demand for accelerated computing platforms, and that's because the total energy consumption goes way down, while as the peak power goes up, right? And that's what this chart in the middle is intended to indicate. But there's much more work we can do to try to improve energy efficiency. I'll mention a couple of topics. They go well beyond just deploying GPUs effectively in your data center. There's tweaks to the clock speed. There's other system level engineering tweaks that we can make to try to have more efficient computing. So for example, rather than operating our technology at peak power, the peak rated power, you could try to operate the technology at something like the peak efficiency, right? And inside NVIDIA, we call this a max Q point. That means that rather than just looking at the performance in terms of time to solution, we might look at the performance in terms of the relative performance per watt, right? And here you would power cap the technology, and you'd end up running at a somewhat moderately higher power efficiency, energy efficiency. Now, whether this would improve or not improve, for example, the total cost of ownership would depend on many things. But if we start valuing energy to solution, these will be the kinds of decisions that we have to get involved in, right? Another is in terms of energy to solution and time to solution, and valuing these two metrics on par. How do we rationalize about time to solution and energy to solution at the same time? Hold these concepts in our mind together. On the left is a scaling plot, strong scaling plot of the Fun3D code, right? And of course, as you start adding resources, the performance improves, and then it sort of flattens out as you would expect. This is typical. You've all experienced it. On the right is a plot of energy to solution, right? As resources are added, the different lines are for different configurations of the nodes. So if we're naive, and we see this is a pointer. Here. So if we're naive and we just want to if we want to minimize energy to solution, we'll always run here at the bottom at the minimum number of resources, disregarding time to solution. Obviously, we're not going to do that, right? But if we want to just run at maximum performance and minimum runtime, then we're up here in terms of something close to 8 times more energy. So where should we run, right? So you can begin to rationalize about this. Think about this. So we said, what about an energy corrected or an energy adjusted speed up as a metric? So here's a normal time to solution for sort of like a one node, or the minimum number of nodes you care about over the running on n resources. And then likewise, if you factor this by the energy on n divided by 1, in the little algebra, you see you were actually optimizing the runtime times the energy to solution jointly. So in this sense, this would be a metric for the and of energy to solution and time to solution. So now they have one joint metric from these two measurements. And in this case with Fun3D, if I put that information together, indeed, one effectively optimizes 1 over the minimum energy and time to solution, right? So we had a homework assignment from the organizers to suggest benchmarks and metrics that might be useful for the future. So this is one such, this is my answer to the homework. Disconnected from this workshop, with some friends at HPE, we proposed the BOF for SC23 on the future of benchmarks and supercomputing to try to get a broad community together to discuss some of these things. And it's scheduled for Wednesday, so if you're going to be in Denver for supercomputing, I invite your participation. I organized this with Rangan Sukumar and Artie Garg from Hewlett-Packard Enterprise. And we'll talk about these kinds of things and other things that the community brings to the table. So talk to me later if you'd like to participate in the workshop, in the BOF. A few additional topics about sustainability. I was also a little jealous of tomorrow's agenda, so I pulled in some sort of other themes. One theme for sustainability and energy is energy efficiency of the ARM processors. For NVIDIA, that means the Grace processor. So here is just a speed up benchmark. NVIDIA's in the green compared to Sapphire Rapids here. Again, here's the power to solution. And so if you look at performance per watt, you see that the ARM-based processor from NVIDIA is giving a nice speed up over competition. So I just point this out to say that energy efficiency is an important benchmark. And this is based on a broad and open software ecosystem that's largely been built by our ARM partners over the past period of time. And so this processor is ready to go from a software ecosystem point of view. Another point on sustainability I'd like to make is the programming models. To program accelerated computing, really, NVIDIA would say the place to start is with standard languages. So C++, Python, and Fortran, and use all of the parallel features of the language that you can, right? Of course, there's very useful portability frameworks and directives approaches that are going to be necessary. These are included Cocos, Alpaca, Raja, OpenACC, OpenMP. The vision that I would see for these is that they would contribute learnings to standard languages, right, over time. The lessons that we learn here can be implemented over time in the standard languages. Therefore, the back reaction on these portability frameworks and directives would be that their role would evolve over time. One would diminish, so the other would increase. Would basically be the vision, right? Emphasizing standard language parallelism, Fortran, and Python. Of course, for innovation's sake, we still need the ability to innovate. And so NVIDIA will still promote CUDA for co-design of its technology processor for speed of light deploying new features that appear in hardware, bringing those to market as soon as possible through a programming model that NVIDIA controls. So that's the sustainability message with programming models. And the last point I want to make is on software testing. So in HPC, software is coming from many different directions. It's coming from a variety of vendors, it's coming from the research laboratories, from the universities, and depending on the partnership that deploys a particular supercomputer, you may have a unique composition of system software. How is this sustainable? It's typically not tested until, this is the old way of thinking, it's typically not tested until the machine is delivered, that you actually get to working on the hard issues of software. This wait until you deal with the hard problems is resulting in very long deployments of supercomputers, very long times for getting the system software working. Another approach would be to focus on software testing and integration at scale on an ongoing way. In a similar fashion that we're talking about working on benchmarks in an ongoing way. There's a role for software integration and testing at scale so that we minimize the new that has to be tested when the supercomputer actually is deployed in the computer room, right? So to conclude, I tried to make 6 points. Benchmarks should be faithful to modern science applications. A more open benchmark development practices would have many benefits. The influence of the benchmark list makers is large. So if you want to have influence, one way is to make a list, right? And energy to solution is a top level priority metric moving forward. A sustainable software strategy should include priority investments in ISO standard language parallelism, C++ and Fortran, and other de facto standards, modern libraries to be sure. And software sustainability of the ecosystem requires testing of the full composed software ecosystem.
Any question? Yes.
Yeah. So I don't really need a mic, but one of the things you talk about when you think about these lists, or you talk about the top 500 or some of the other benchmarks, is the benchmarks also need to be scalable. One of the nice things about HPL is it actually scales to machines from your laptop to the top, to the number one supercomputer. And when you go to the next one, they didn't rewrite the benchmark. They obviously coded it to the system, but they're able to run fundamentally the same benchmark. One of the things we see with other benchmark challenges, and we were talking about this over last night with AI, is getting benchmarks that actually scale to different sizes is a really big challenge, because fundamentally, especially with some of these AI ones, you don't actually compute the same problem as you scale the problem up. So I think one of the opportunities and open challenges is how do we make scalable AI benchmarks? Thoughts?
I'm advocating for more work on benchmarks in an open, public way, so you're contributing to that argument.
Another question?
Thank you for your talk. I want to ask you about grace. I don't know really, is it something that is different from VH100, the follow-up of VH100? Can you tell me more about grace?
Grace is a central processing unit. It's not a graphical processing unit. It's so NVIDIA's first server class CPU.
Huh.
Okay. And it's coming to market in the upcoming weeks.
Okay.
Yeah, and some people here will be receiving them. It's also paired with Hopper in a Grace Hopper super chip with a very high bandwidth interconnection between the two.
Yeah, like the NVLink or something like that?
Yes.
Okay.
Any other question for Jack?
So you talked this, point 6 where, right, this kind of integrated testing, we need to kind of test the full composed software ecosystem and stuff, right? One of the challenges we had with that is that, we test your software after the fact, when it actually gets deployed. Sometimes you only can test it, after it gets months later, or even in some cases years later on Sierra and Summit deployed on these systems. Is it possible that, that we can do more around vendors actually including some of our software in their testing procedures before, they release it, so that we don't just report bugs, and regressions after the fact? I think there would be a possibility to do that. One of the challenges is the infrastructure is for this. We need to rationalize the infrastructure to perform such benchmarking. But I think NVIDIA would be open to that, and we recognize the challenge that you just articulated. And it's not unique to Summit and Sierra. It was true with Titan, and it was true with Summit and Sierra, and maybe even with the current generation of machines.
Possibly.
Okay.
So you made a very good point about programming models, how the way to go would be to stick with the standards, C, C++, and integrate what comes from the high-level programming models like COCOS and so on into these standards. I was wondering, what are your thoughts about CUDA, how this could then flow into those standards? Because one thing that CUDA is an excellent programming model, but it has created also some kind of a fragmentation, if you want, in the way applications are developed for specific targets. So do you foresee including some of the CUDA features in the standard models and pushing from the NVIDIA side to adopt those?
So I'm not sure I understand the fullness of your question, but I don't anticipate NVIDIA giving up control of the CUDA programming model, if that addresses your answer. But I do think any alternative or competitor technology to be competitive in the long term will need their own CUDA, will need their own way of co-designing and moving quickly to deliver to the user the hardware features that they innovate. And so I would expect these kinds of developments to emerge with the alternative technology providers.
Any other question for Jeff?
I'd like to know about your opinion about domain-specific benchmarks. And in Europe, there's kind of effort to create this kind of domain-specific benchmark from flagship applications from different domains. And from these flagship applications, we try to extract many relevant pieces of code that are, relevant and the associated test cases for the scaling problem also. What is your opinion about this kind of initiative?
I think I understand what you're talking about, but could you just give an example so I make sure I'm aligned?
Yes, for example, there's a benchmark suite called HPCW that is not really well known, as you explained why. It's a set of piece of code extracted from weather and climate models. So they represent really specific problems of spherical harmonics or radiation, these kind of things. And this kind of benchmark and mini apps represent the needs as much as possible, at least try to be relevant for the community, the weather and climate community. So this creates kind of domain-specific benchmark, in my own opinion. So what is your...
My opinion is that this should be encouraged, and that would be very helpful. That accelerated computing essentially happens one domain at a time. This creates a tension between the general purpose nature of supercomputing as we've known it and a future that's much more domain specific. Estella's talk, I think, maybe was the best one I've heard about talking about the balance of issues when one deals with this, and we just have to deal with it. Certain programs will be able to prioritize a domain. Supercomputers are being deployed for weather, right? And so one need not focus on those projects need not focus on non-weather priorities, right? But other programs have a mission that prioritizes much more the general purpose nature of computing. And as Denard scaling ended in 2005, and Moore's law has sort of ended now, and progress comes through full stack optimization and maybe domain-specific accelerators, this will continue to be a challenge, right? And time will tell where the progress happens, but investment in valuable applications like climate and weather is surely to happen. And so I think I would encourage domain-specific benchmarks.
Other question? Maybe more comment on this. Maybe more comment for the energy to solution. Thank you for the homework. Maybe just a comment is that energy to solution from one machine to the other. You don't have necessarily the same information. In one machine you can have a CPU energy consumption, and another one you can have the CPU and also the switch. And sometimes as a user point of view, in the Slurm log you just get a number. but you don't always know what's behind the number, what components you have in this energy. So I agree clearly this is important, but this also requires to make sure you give the full list of what has been retrieved in this energy consumption number.
This is needed. I will highlight that the National Renewable Energy Laboratory in the U.S. has a DOE grant through the Cooler Chips program to standardize the testing of server class resources. NREL has a very good reputation for testing the efficiency of photovoltaic cells, and their vision is that they could grow the capability to test server class computers to the same level of quality, so that it's the standard, they would aspire to set the standard for testing energy efficiency. These kinds of things, there's clearly an opportunity for these kinds of developments.
I think it's really needed, because again, in my experience, I saw sometimes, so again, in the storm you get the number, but on this machine, this is just the node consumption. On this one, this is the node and the switch. Sometimes you have an aggregation of the data, and you don't know about how the aggregation is done. So if you don't have the explanation behind, you cannot just compare the number.
Yeah, this would be consistent with developing subject matter expertise in this topic.
Thank you. So, thank you very much, Seth. And our next speaker is Ludovic Hainaut from Eviden. Ludovic will present HPC and AI benchmarking, workflow and objectives. Minute, the time I retrieve the slides. In the meantime, for all the speakers, please don't forget to send me your slides, please.
Hello, hi everyone. So Ludovic Hainaut, I'm Head of Application Performance at Eviden. So the BDS, HPC, and AI Quantum Business Support Kit. And I will discuss about the HPC and AI benchmarks, the workflow, and the objective. So I will go quickly. Two parts: how we see the work of benchmark, and then what are the objectives, because I think that's one of the key points to define what is a good benchmark activity. So it's typical for benchmark activities, so we don't see it's in white at the start. So there is a big activity to understand what is the requests, and then to plan the activity properly. So for me, it's the most important part, and we'll go into details in the next discussion. One first part, and we see there are a lot of going back and forth. The first part is the source code modification. So at first we don't do any source code modification. We do just compilation. Usually we use the flags provided by the client. And we do a first execution. We do a first estimation of what it will be on the next system. We discuss with the architect to define the best system. will it be CPU, GPU, or whatever. And then there is a big part about reports and output files. They come back to it. So at first we do what I said as is baseline. So from that we can start to work and to see what we can do to enhance the solution that we propose. Then we tend to do basic profiles, so we see how the system or the application behaves. It will help us deciding if we change some code, if we change some flags, the way we execute the codes. So everything we can get as information from these profiles will help us to decide what we do. And at the end, we try to do targeted profile. So the loops that are taking most time, we are putting additional metrics to get information and to try to optimize them. So overall, benchmark activity is typically 6 to 12 weeks. So we don't have time to spend a lot of time typically to port the GPUs or stuff like that. And I will come back to it. A big important part to have a successful benchmark, especially now there is a big lead time for delivery of system, is to work with vendors before, so we can be prepared and we can plan for the infrastructure and everything that we need. Part of the benchmark, something that is hidden from everyone, is that there is a lot of work, a lot of preparation required. You cannot just get a benchmark and run it. You need the system to run the benchmark. So the sooner we have an idea of the size of the cluster, we can build it. So either internally or work with partners to get large systems. One point also is to work with partners to have sample nodes. So typically for the Hopper technology, we work with NVIDIA to have this sample and to see how it performs. And then work with all technology partners to understand what is the roadmap for products that will come next year, in 2 years, 3 years. It's an important part of the work that we are doing. Also, the methodology. So we talked a lot about NPI directives, a little bit about cloud. Container arrives. Typically, there is a remaining question. Do I do my MPI inside the container or outside the container? So all this kind of stuff we are trying to figure out for the next generation system. So the plan is either to get something that is very efficient, effective, or you lose a little bit of performance, but you run in container and you can move it easily everywhere. It's all a problem of productivity. So in the workflow, one of the most important parts for us are the start to understand what the client is requesting, and at the end, what do we put in the report. For me, the most important part is to provide a comprehensive document. So we explain what has been done during the benchmark activity, and we justify the extrapolation for the application and the projection of the system. So it's all a question of the application, and you will see I will talk a lot about application and not benchmark, because for me benchmark is even bigger than only application. So the application is only a part of the solution. Something that we always forgot as technicians is the price, and it always comes in the picture. If you have infinitely deep pockets, you will not mind about what solution you get, you will build anything. So it's always a discussion from the vendor, in the vendor to optimize the application, but to see something that fits the solution with discussion with the architecture. Typically for the architecture, about 15 years ago, I was working with another company and I saw people going out with the pipes and they told, no more water in data center, we don't need any water-cooled system. I said, oh, when I will need a system like that, please come back with a solution for me. And 5 years later, they built me a specific pipe that was able to cool my water-cooled system. So it's always a question to understand everything that comes into the picture to provide the best solution. And don't be fooled, the purpose of the vendors and the partners is to maximize the price they will get. And I will come back to it. I think it's an important thing to keep in mind. So for me, the best practices, I won't go too deep into that. It's just my takeaways for you in terms of what a benchmark should look like. So it was a struggle for Jupyter benchmark, for some of the one exascale extrapolation, how it behaves, and so on. But typically, what is good to have is something that is ready to use. And if you are using ISVs, please negotiate with the ISV before, because it helps us a lot to get up to speed. In the past, we were just requesting to the ISV a license, and now it takes months to get them. So, yeah, it's a few hints of what we think is a good approach to what is required. And another point, which seems ridiculous, but if the application and the system specification are not agreed in the client side, then it will end up with something that is completely non-viable. So if you provide non-GPU application and request GPU-only system, it's unlikely it will work properly. Well, NVIDIA will be happy, they will have sold some GPUs, but you won't be happy with the results. So for me, the benchmark activity, the pure benchmark activity is only a small part of the overall activity that is ongoing. The big part is understanding the needs, and the last part is defining the best solution. And as we'll talk after, I think the big part is how the benchmark package is provided. And I come back to the essence of the benchmark. So what we call benchmark is coming from what we use to test cars. So we put them on the bench, and we have a score, and they say it's a benchmark. So yeah. But it's not clear what is benchmarked and what is the results, what we are looking for. I like the word from Estela this morning. It's moving targets. And yes, both systems design and application will evolve, so the criteria will change. And if you are not very specific, you can end up with very difficult solution. So the kind of metric we have in the past was pure performance. Then it comes to performance per dollars or per euros. Now the metric is performance per watts. And depending on what we define in what are many different vehicles. So we'll come back to the story to bring a child to school. If you are alone, then a race car might not be that good, but a regular car can be great. And if you have about 20 children to move to school, you will use a bus. So depending on how you define your benchmark set, it will change what you will get. So it's very important to mention. And in the teal, in black, it's a different kind of bench you can have as well. Because when we do the optimization of the application during a benchmark, we change the application. So if you do not set appropriate expectation, direction on how you want it to behave, at the end it can be completely different from what you proposed. Typically in Jupyter it was clear, no code change, so fine. But it's something that is important to understand. Typically, most of the work we do in benchmarking as vendors is to optimize the compute time. But we might lose sense, the physical sense, the science behind, and it might not be fit anymore for good activities, good science. So here it's an example of what we do, because I done a lot of talk, but not too much about what we are doing exactly. It's an example of changing the scope of objective from pure performance to energy to solution. And here it's the example, so it's Cineca Leonardo with GPUs. So here we have 4 applications, and playing with the frequency of the GPU, we are able to get better performance, better energy to solution, without decreasing too much performance. So here it's the optimum we found. So Jack shows the curve that we draw, and here it's the final answer that we get. So just playing with the frequencies of the GPUs and CPUs, we're able to decrease by up to 15% the energy to solution, while only decreasing by 3% for quantum mechanical crystals the time to solution. So it's something that is very important to keep in mind. And that, I don't have a point, but I forgot. Yeah, so that's the point. One other point also is here it's pure, as you mentioned, Stella, it's as you found, about the criteria we took. So here it's only the network and compute nodes, and it does not take into account the rest of the data center, the storage, and so on. And there is also another aspect. In some cases, the clients are reusing the energy, and sometimes they want the system to produce heat, so they can reuse it on the offices to get a little bit better air during the winter. So it's a big question. So for me, the takeaways, main objective for us as vendors is still to fix a contract. So that it is harder to, the harder it is to estimate the performance, the higher the vendor risk margin will be. So if you are unrealistic on how you set the benchmark, you are asking to run at 10 exaflop typically, only from 1,000 nodes, then we take a lot of margin in terms of proposal. And the margin is money, and money will come back into fewer nodes, fewer compute capability. So it's very important to have clear benchmarking score, so you can ease the work of the vendor and you can compare things properly. The benchmark should represent what you are expecting. So we're talking about 500. It's a key metric, as everyone mentioned. I think it is de facto the standard in HPC industries, but it's not what you will run on a day-to-day basis on your system. So it's very important to balance it with some benchmarks that will represent what you will get, what you are expecting to get, what are the needs for the applications. So it's something I think that is the most complicated part as client, is to be able to understand what I will need in the future. And as Jack mentioned, the vendors are open to discussion for future technologies and timelines. There might be physical challenges, technology challenges that will change drastically what is happening in the future, and it will impact a lot the way you compile applications and other stuff. So I think it's very important to go and discuss with the ecosystem to understand how to go forward. That was the end. I don't know if you have any questions.
Thank you, Ludovic. Any questions from the audience?
Thank you very much. Good presentation. I'm So you mentioned such kind of benchmarks for the carbon neutrality. Do you have any idea to measure such kind of carbon neutrality? First place is it's completely depends on which kind of electricity there some contract. The second thing is some simulation results can make some good reduction of some carbon. So which kind of idea to make some carbon neutral?
Here it's more for the carbon aspect, it's more the overall workflow of production of systems that you have that will be taken into account. So the major part is the power consumption, but there will be also how you build the chips. If you have factories that are carbon friendly and this kind of stuff. It's part of a complete workflow. But here it's a little bit more complex to address and to score. Yeah, it will be great.
Other question from the audience? So thank you for raising the point for the energy, you write storage system and everything. And indeed, you can measure CPU time, the compute, and you have the data movement and everything. And just a comment also on your time to solution versus energy to solution. That's clearly important. But from a user point of view, somehow this would have to be automatized, because you cannot know that for this test case you need to decrease at that level the frequency, and so that implies also some other, not black box is not what I mean, but some automatization that has to be also explained.
Well, yeah, actually that's a very good point. I think here it's benchmark activity, so we are doing the work, we have a specific objective, but the scientists, they want to have their solution fast, and they don't pay the bill for the electricity.
Not yet.
I think it will be a good point to make them pay, because, or to have some incentive or whatever, because they don't see that aspect of energy. But if they are, I've seen on some systems they start to give priority to people who are greener than others. So that's one idea to push people to be more resource friendly.
Yes, being greener is because again, if we just take the energy consumption, you can have a very small benchmark versus very large application. So it's not, you cannot also just take this to compare different usage. I think users are more and more aware of the problem, because the possibility that we pay through the with respect to the energy is closer. So we know about, but maybe there is a gap on knowing about and being able to act on it. Yeah, the gap is, there are many steps.
If you are doing always the same tests, then I don't think you need a supercomputer, because all tests are different. We need to have some abacus and to give some, to take a decision at one point. It will be similar between applications, but not the same, and you will need to convince people to run at lower speed, because we think it's the best solution. And if you spend time, if each time you need to optimize an application, you reduce the activity, maybe you will waste the same amount of energy, so it wouldn't be a benefit at the end. So you need to find some clever way to do that.
So that's a new paragraph to add for the white paper, but I didn't answer that. Thank you, Ludovic.
Hi everybody, I'm David Lacombe from ARM. I'm responsible for the HPC business that we do at ARM, and I'd like to present a few perspectives on HPC benchmarking. Some thoughts I put together over the last few weeks in anticipation of the event, so pleased to be here and talk through some of those with you. Also like to thank Conrad, my colleague Conrad, who's very helpful in helping me get these together today. So firstly, I'd like to just introduce ARM, because I think the perspective of what we do kind of informs some of the slides that are coming up. So ARM is a semiconductor IP licensing company. We don't actually make chips, but we design the cores and the system IP and some of the configurations that would enable our partners, what we call our silicon partners, to design and actually build chips. Or we also license the ARM ISA, so some partners can actually build entirely their own design based on their own cores and whether either third party or their own system IP, etc. As a business model, I'll talk about how that works in a moment, but it's led to some significant shipments over the years, and something over 250 billion chips have been shipped on ARM architecture to date, and around about 30 billion a year. 30 billion devices shipped a year. So our business model, as I mentioned, we're all about licensing the IP. So our partners would pay a fee for the license and then a small fee in royalties for every device that's shipped. So what that does is it gives us this vested interest in people being successful with what they build. It's not just about the license, it's about them going to volume and being successful with that product. So whether it's energy efficiency or performance, you can see it's in our interest to do a good job of that. And if we look across some of our partners and what they're building, just in the world of HPC, things that are either been built or being built, etc. Well, Fujitsu designed and built the A64FX processor, their own core, their own mesh, and a fantastic chip there, which was then deployed in Ricken's Fugaku system, which was #1 for 2 years in a row on the top 500. It still leads on a number of benchmarks, such as it's the highest Green 500 CPU at the moment. It's also still the #1 for HPCG, so well done for that design. They were able to introduce something with a terabyte a second of memory bandwidth. The Ampere built something with 128 cores on a single SoC, based on one of our Universe N1 cores. And more recently, we see NVIDIA about to make available the NVIDIA Grace CPU superchip, along with Grace Hopper, as Jack was talking about earlier. And NVIDIA was able to bring to that design something that they couldn't have found anything off the shelf to make, basically to bring out a product that would fly for HPC, but would also help what they were doing with the GPUs as well, bringing things that gave even more capability to their GPUs. But they brought in low power LPDDR5 into that, and actually going onto the package. So it's not the standards on DDR5. It's actually got this low power memory, which is enabling them to bring out a really energy efficient processor. Also, in other spaces, you see NVIDIA's Bluefield adapters that are using ARM cores. Obviously, a very different design from other sort of CPUs for servers. They've got a different purpose. AWS, they developed based on our Neoverse V1, the Graviton 3 processor. And we're able to bring out something which is the first DDR5 systems in their entire fleet, if not the entire fleet of all the clouds. They actually deployed and made those available sooner. So that IP licensing is kind of all about flexibility. But yet you've also got the standardization of ARM ISA, and the standards meaning there's this compatible software ecosystem. So let me move on to the actual topic of benchmarking. And I think there's a lot of commonality with what I've heard earlier in the talks. Why we benchmark? And I think the top reason for me is it helps us to improve product performance. But we see benchmarking at all sides of the buying process, when people are designing systems, when they're bidding, when they're being selected, when a system's being accepted, did it hit the numbers you promised, etc. And of course for marketing, and then for publications. So there are lots of reasons that people want to benchmark. So take a look at what can be done with benchmarks from our perspective. And over on the left-hand side, we see, as I mentioned, ARM licenses its architecture for people to develop their own processors, as well as that architecture landing into our own cores, which we subsequently license. So we have to be able to have some form of estimate as to whether it makes sense to add, say, some new instructions or some new whole instruction set to the ISA. How do you do that without data? When we're designing cores, it's important to be able to specify and size what you need to achieve the performance, and what we mean by performance. And we also need to be able to analyze the performance we're seeing as that design continues. We have other partners who would take some of our IP and build a system with it, whether we're talking about a system being the SoC, which, say for example, the NVIDIA Grace, which is 72 chips on each of those two halves, 72 cores on each of those two halves. How do you parameterize and build the right system? How do you choose how much cache to put in there? How do you choose the various settings of your mesh or many other things in there? So there's a role for benchmarks there to actually help you build a good system. Or even to look at it and say, if I choose this cache size, or if I choose this number of DDR5 channels, what am I either giving up, or what am I going to win with that? And then the final place, which is actually the one that's probably one of the easier to impact, because you can actually do it on real systems, is fixing things in software, whether that's the application itself, or in the math libraries, or the compilers, or some other ecosystem area that needs some effort. And if you look across the spectrum of time, you've got the actual systems on the right, where things run in the real time with the application across. And you go right over to emulation, where you're not talking gigahertz anymore, you're talking kilohertz, and things, you really have to get things down to the tiniest of kernels to be able to sort of simulate and really understand, say, the pipeline model of a core, or the traffic that's going off on a mesh. So you've got different perspectives, different times in that cycle, not just how long it might take to run various parts of a benchmark, which therefore says which benchmarks you could actually ever do or couldn't, but also the time at which something could have impact. For example, our architecture, we tend to add things to our architecture. Let's say it could be between 4 years from something going into the architecture to it actually arriving in some of the systems. Because you've got to go through that standardization process for the architecture, through to actually building the RTL of a core and the system IP around that. Then finally a partner would take that IP, they may have been getting some early beta drops of it, that kind of thing, but they would then build it, it would go to a fab, 6 months later it would come back in silicon, they'd spend some time bringing that up, and then finally you get it. So there's a big lag between them. So sort of speed of light might be for 3 years in that perspective. The thing that you can actually change things today with is, of course, software, where you fix it and it's out on hardware today. But this kind of timeline is really important. So if we look at the high-level fit of benchmarks, how they fit into the whole development of IP and ultimately products. Well, HPC is part of the infrastructure segment arm. So we're an input amongst many to the architecture, which applies for not just the infrastructure segment, but also everything we do, whether it's in the mobile space or automotive and other areas, through to the IP and the engineering processes. So in the server space alone, we're sitting alongside the hyperscalers, but also actually hyperscalers do a lot of HPC workloads, or their customers do. 5G, networking, many other workloads. So we use that input as part of defining the roadmap for our sort of highest performance cores, which are kind of aimed at more HPC-like applications, that we call the Neoverse V series, right through the high throughput cores, through to highest efficiency cores, which might go out there on some base station, for example. And then we'd use that input could also go into our system IP, the mesh, for example, or the MMUs, the interrupt controllers, and so forth. We'd use it to size up and build some of the pre-configured IP, which we announced recently, the compute subsystems, the CSS as we call it. And finally, what we do in terms of toolchain. And we can measure the outcomes from the benchmarks by power and performance at various points in emulation, and ultimately when people actually have silicon as well. But there's a final challenge which comes from that business model. So many of the performance-defining characteristics of what are actually chosen, or they're configurable by our partners. We don't choose how much L2 cache someone might put down. We don't choose how many cores someone might want to put onto an SoC. We don't choose what frequency they might want to run at. That's, so it's a bit of an extra challenge. So I think it's really important that we have good benchmarks, but kind of what should be benchmarked? What makes it a good benchmark? What is it that HPC cares about? If I go to 50 different HPC sites, I'll probably get 50 different answers. Particularly if I spread beyond sort of the university or the government sector and start moving out into industry or some other areas like biosciences. So how do we get that information and how do we know it's right? So we actually go and look at sort of approximate sizings of the markets and the workloads that are run. What share of HPC is running CFD, for example? And we get that data from analysts like Hyperion and Intercept 360, along with our silicon partners, we call them SIPs as we call them, silicon partners, OEMs, the HPC sites, and then of course the ISVs who are developing their software for some of these markets. And from that, we take we try and get a representative code, a proper workload, or more than one proper workload from each of those segments. So we're making sure we don't miss out on things. So it would be very unusual in a government HPC site to be talking about computational finance. Genomics will be huge in some sites if we went to talk to them. It's also a very, very large workload in the cloud. Weather is really important to a lot of national sites, but equally it's a very interesting workload for the cloud. There's a lot of people out there running WARF and other weather codes for commercial reasons. So you have to really understand and try and figure out the size of things, and the data is not perfect. That is actually a big problem. In fact, if you look some of the data out there, would sort of classify, they say something like 25% of HPC is government. Well, that's great, but what are they running? It doesn't really help you design a chip. Another purpose, of course, of benchmarks is marketing. We've got to demonstrate performance for people to be interested in it. And that could be performance, or it could be performance per watt. We know real workloads matter a lot to industry. Artificial benchmarks less so. It's interesting to actually look at how some of the silicon vendors and cloud vendors and sort of system integrators will do marketing around some of their products. There's actually a very broad consistency. For example, Azure, AWS, most recent launches of instances they've got GROMACS, LAMPS, NAMD, WARF, some finance, as well as closed ISV codes. So, for example, Fluent, Dyna, and Star CCM Plus are very often in there. And so this consistency is actually very interesting. Trust is a huge thing as well if you're going to do marketing. Your reputation's on the line if what you put out there is not a real genuine test case. It's really important to a company, but also the individuals who put that work in. You want to be a bit proud of what you're doing. So is that test case that's being marketed something that's particularly been selected, a data set that perhaps fits into the L2 or the HBM or something like that? How do we get objective data? And when you really went all out to get the performance on your platform, perhaps you used a particular math library or a particular compiler. Did you try that for the other side as well in that, if you're going to do comparative marketing? So you have to be fair. I think that's really important. Or reproducible. I'll talk about that in a minute. I was reminded while putting this slide together of the, I think, the 12 ways to fool the masses when giving performance results on parallel computers, which dates back to 1991. So I remember reading that in the late 90s, and that's a good read. It's really good. There's a URL there, or just Google for it, and it still applies today. It's great. So turning to what I'd love to see, what makes an ideal benchmark suite? Firstly, a build process that doesn't require a PhD in CMake. I can handle make files, CMake. Or a rabbit hole, a recursive rabbit hole of dependencies. You don't want to have to go off and find this package, this package, this package, and then all the configuration for that just to try and get there. And I think, listening to the talks earlier, particularly from Eviden and from NVIDIA, you know, the amount of effort that goes into benchmarks, it's substantial. And to actually running benchmarks for procurement, it is substantial, and somebody's got to do that work, so let's make it easy. And a test shouldn't depend on domain knowledge to run it. If we're going to take a HPC code, let's say that's WARF or something, a proxy for the weather market, by the time you've reached the CPU engineers, the people doing the processors, the IP for the cores, or the architecture, they don't know much about the weather and how to calculate, about how to calculate the weather. I think we all know about the weather. So, you know, you've got to make this easy to actually reproduce without being a domain expert, which means, you know, how to make sure you're not just running a completely inadequate or incorrect data set. Good documentation, good data sets, open code with a benchmark subdirectory. There's lots of ways we can do good jobs at this. And also, it should be clear when it's not working, you know, someone saying, oh, that didn't converge, it was a wrong answer or something, you know. There's no domain expertise that, you know, that you can rely on. We're trying to make this easy to be able to get the right performance. It's important to be able to, concurrency and reproducibility is hugely important. So tests shouldn't go stale. They should be able to be based on the latest compiler. They should work on the latest compilers, tool chains. They should also use the latest dependencies. And it should be easy for other people to contribute to a benchmark project, fixing it, you know, get those old pull requests in. It should run across as many platforms and architectures as is appropriate for, you know, for today. Should be able to run across the compilers and the libraries that are out there. There are multiple options there. But then the problem with that is, of course, you've got who's going to do the CI for this, who's going to maintain the suite, who's going to fund the suite. So it's a right sustainability kind of question here. So it really does link in with tomorrow's sessions. And then you want to be able to reproduce things, so just getting some good fingerprints in there of what dependencies, tool chains, etc., that's really important. And I think there's been a lot of progress in this world. Some of the things like SPAC and Reframe have been hugely beneficial to the community for actual applications, but the impact is there also when you come to benchmarking. So we've moved along a long way in probably the last 3 or 4 years. Relevance is important. Benchmarks should be about today and the future, not the past. So do you know what workloads you're running on the system now? And do you know what the system's going to run when it arrives? And from the perspective of building IP, you know, it's you know, the design that could have a 2, 3, 4 year lag before it lands on the system. You have to really be good at predicting what you think something's going to run. And, you know, if you've been asking for something since 2008, is it still really the right benchmark? Or longer? We're, of course, with the benchmark whose name I'm not going to mention today. I prefer real workloads too, because I just I think it's more important than proxy apps in the first instance, because it's too easy to do a proxy app that isn't realistically representing, say, the memory bandwidth or I/O factors. And if you do proxies, just make sure it connects back so we can say, well, this is important because this appeals to this part of the HPC user community. You know, if you're good at X, then, you know, then the whole of engineering is going to love you. That's really important. But I think there's something we could all do, all the HPC sites could really help with. I've always found it really hard to figure out and understand which workloads are running. So publishing workload usage across the system would be awesome. I think I only know about one site, Archer in the UK. I'd love to know others. They actually do a status thing listing by CPU hours which applications have been running this quarter. There's a lot of A.out in there as people have compiled their own applications, but you know, you can look and you'll see VASP, you'll see OpenFOAM, Be like, yeah, oh, that's this, and this, and that's really helpful. Gives you a good view as well about scalability of what people are running at. And I think across some of the larger organizations that are responsible for buying an awful lot of HPC, be that in the US or in Europe, there's data there. It'd be great to see it and share it, because I think there's a good benefit from the vendor community having access to that kind of information. If you want HPC to look better, help us know what to fix it for. Just aggregating it across all those institutions would be super helpful. Finally, of course, it's necessary to have a range of scale across even what we do. We don't build out great big clusters ourselves, but we know obviously folks like HPE and Eviden will do that and do have the ability to sort of profile and run things at scale. All the hyperscalers too. So you need the large stuff, you need the small stuff, and you need the very tiny stuff. So we do need to do massively shortened runs for emulation. We can do post-silicon, which on real servers will get our partners' hardware, or we'll take some time in the cloud or something like that, and we can work on bigger cases. But we're also never going to put a 1 hour, 1,000 core job into the CI process. It's expensive as running a HPC benchmarking through sort of regressions and things like that. So, yeah, I think that's all I wanted to say on that topic. And then just to sort of quick wrap up of where we are in terms of those benchmarks and a little bit about the process. Well, over in the world of actual systems and software, as I mentioned, I think the community has really helped through doing things like SPAC and Reframe. The adoption of things like Ansible has been really helpful. It is easier to get a benchmark suite going these days. We wrote our own, and I think that is a problem. It would be great if there was something more open source and usable that we could just all rely on and therefore trust the data of it and reproduce what other people have done. We shouldn't all be reinventing wheels. I think we find it easier to contribute to a project that existed than to share something we'd already done, for example, but I just think it would actually benefit a lot of people. From that run of Ansible, SPAC and Reframe, where we iterate over all the compilers, all the platforms, the OpenMP thread count, the MPI process count, just to try and find the best combination, we can do things like we can fix the compiler when we spot a bug, and we've spotted a few over the last sort of 18 months where we've got this rig really in place. And that's led to the compilers getting better all the time. But we'll take the data from that in a great big Excel spreadsheet and come out with a really nice fit of sort of how the performance of a partner's current silicon is, but also things like what the PMU, the Performance Management Unit, the hardware counters are telling us, which gives us good sort of aggregate data about the importance of memory bandwidth, for example, or the behavior of L2 and those kinds of things. It can help us know more about the prefetches and the stalls. Collated data is really, really, really helpful. So it's really helped us then, and we can talk to our partners and say, but if you do that, that's a good decision, that's a bad decision. We think this is how you can really win in HPC. And then, of course, we take some of that into microkernels and loops inside our IP, and very similarly into the architectural features. But it all starts over here, and what we're trying to do is really connect what we do in this side of the world much more strongly to what's over on the left-hand side. So in conclusion, benchmarking is important to drive better HPC. I'd love to see an open maintained suite. There are many, well, and there's a problem, there are many suites and legacies of projects that have just tried to do exactly that. So I would prefer fewer well-maintained, widely adopted benchmarks than those that just sit there sort of bit rotting. And maybe, with all the progress that's been made over the last few years on other projects, it could be it's the time to actually do that. So, thank you, everybody.
Any question for the leader?
Have you thought about what could be done to fingerprint the jobs to make it easier to collect requirements? So this 8 out problem, right?
Yeah.
So when a.out runs, it actually prints the first line of the name of the code.
Yeah, that could be, definitely. The guys in TAC, or part of the XC project a few years ago, had Exalt as a project that was trying to itemize a lot more of things that were running inside things. Even at the level of, does this code use degens? What bits of the performance libraries does it care about? I think there's stuff that could be done there.
Yeah. It seems like more could be done to automate the solution of the a.out problem.
Yeah.
I think no one's really tried to solve it, I think.
It's true. I mean, you do have the whole confidentiality thing as well. I know some sites would, but then, you know, a.out is just as revealing as anything like it, I guess. I don't know, but people should be aware that you do it, and then I think there'd be no reason for not publishing what's going up there. And I just think we've got to be more open about that data if we want to drive improvement.
Any other question for David? So, thank you for doing the homework. This presentation.
Performance modeling for future platforms. So basically this talk will mainly address this angle to discuss basically what we need in terms of benchmarks, what is the best way to influence future products, and some, let's say, limitations of current approaches. So, just a cartoon to give you a bit of context of the kind of configuration we are trying to address. So, obviously there is no product description here. It's just an illustration of what we are trying to model at the SoC level with an increasing complexity in terms of tiles, in terms of chiplets, in terms of the hierarchy of caches, etc., etc. So usually this SoC-oriented modeling activities is not fully aligned with this sort of, let's say, exploration of configuration at scale. And one of the, let's say, challenges I will highlight is really how we can kind of connect those two types of activities. Usually at this level, people may really focus on the compute aspect. So, for instance, David mentioned this, let's say, the impact of low-level modeling, the fact that you need to evaluate low-level features, could be from the ISA, could be from even the software stack, etc. So this is one part of the modeling. Obviously, the objects we are trying to model are much more complex, and to be honest, I do see that the uplift people may expect to build next generation system are probably not only at the ISA level. I mean, there is this AVX10 introduction from Intel. There is an advanced, let's say, reorganization or contribution in the ISA from ARM also. But this is only one part of the modeling, and there is an impact that is probably much more important at our level. As an example, the memory technologies, that is clearly something you really need to model. The iodide that will that will basically influence the way you will be able to design the scale up and the scale out of your system. And all those, let's say, configurations should be representative, should be aligned with the benchmark suite you are trying to, let's say, obtain from the partners or from the customers. So one of the main challenges usually here is the programming model. So if you are working on a system that you expect to design for the next 3 to 5 years, you expect the programming model to be, let's say, roughly aligned with the suggested configuration, but you have no guarantee. And the benchmarks you may collect from the partners are, let's say, 5, 10, 15 years old, maybe based on old type of design. So it's usually a gap in terms of what you want to model for the next 5 to 10 years and what you can get from the partners that is probably 5 to 10 years old. At scale, because it's one of the challenges to maintain some sort of common view between this SOC level activities and what is the impact at scale. As an example here, you have the traditional glueless versus switches configuration, and one of the way to take this into account is obviously the IODI, and this IODI will basically influence or impact your capabilities to scale and the number of switches, etc., etc. So the application you may identify to build your system is of high importance in terms of, let's say, the type of modeling you will be able to deliver. So, in terms of process and the way you are usually designing a product, I mean, it's similar for most of the vendors. During the exploration phase, you mainly need the micro-arch simulator, both for functional and performance type of activities. And one of the focus is clearly mini-app. Basically, we have probably too many of them. With so many different benchmarks coming from ECP, coming from so many different communities, but we know how to handle them, and they are quite interesting in terms of exploration, but for the next phases, we probably need something else, because we need to scale in terms of size of those applications. Could be kernels, could be full application with distributed memory, and full application, accelerated or hybrid application. So the process here is clearly aligned with different requirements in terms of applications and in terms of benchmarks activities. One thing also of importance is we should keep in mind that an application is a combination of communication and compute. I mean, that's why the mini-app aspect is really important in the first phase. But during the process, we need to address the communication plus compute capabilities. So one of the challenges is to consider a very simple method where you don't have asynchronism, when you are not considering overlap. But in reality, most applications are designed to be efficient at scale, including overlapping. So you have a diversity of approaches for the tracing of the communication. Could be aggregation. You can use your favorite library or framework like SCORP. You can use Intel, APS, etc. to collect data at the distributed level. In terms of modeling, you can start from very simple analytical model like log-P, and you can address some advanced capabilities with SimGrid, SST that are event-based frameworks. And the compute, it's usually the traditional approaches based on hardware counters, and the modeling can reuse analytical models and obviously cycle-accurate type of frameworks. So one very important aspect is the scalability of your method. So how to move to new benchmarks and new applications. It's not, one good example is AI, probably. It's not because I have to say AI, but it's because most of those frameworks are not MPI based, they are different, so how you approach can really be adapted. And in that case, those approaches need to be high level indeed, so they need to be flexible. So one interesting description of the landscape for shared memory systems. So LTL-oriented simulators, typically that's not something HPC people are really, I mean, we are not, it's mainly for verification indeed. We don't really have to consider that scale. We really have some contribution for nearly accurate simulators and things at the user space. And this is how we can really explore loops, specific loops from HPC, architectural exploration, etc., etc. So the accuracy is usually orthogonal with the speed. So you see here the number of instructions you can really process in 1 second. And there is an obvious limitation for large-scale applications for user space type of frameworks. So, as said before, in that case you need to have a plan B, and you need to have something in your back pocket for, let's say, scenarios, to have an idea of the impact of features A, features B, etc., to really understand where you are going. So one of the tools that is probably well known from the HPC community is the RUSHSAPREM model. It's very simple, but it's based on a very strong assumption. I will comment on this later on. So this RUSHSAPREM model, basically based on the arithmetic intensity, is based on the assumption that between your current platform and your future platform, the overall efficiency would be overall the same. And it's probably too strong, but it's a way, at least, to explore things and explore the impact of some changes in terms of high-level ingredients. This is just an illustration of some work from my former colleagues, Conrad, and from folks from CEA, working on the ARM instruction emulator and Dynamo Rio. And in that case, you can derive few info from those graphs. This is just a tentative to say, okay, from a naive N1, so David described the Neoverse roadmap N1 or TX2 platform, what can you expect? Adding some HBM2 or SV512 sort of vector instruction. So all those data are probably wrong. I mean, but what is important is to have some sort of indication, to have some sort of trend, to understand where you are going, and after that you can probably build something more accurate to really explore what's going on. But again, we are in the context of what-if analysis and the impact with respect to application. Another thing that is, I would say, of interest for what-if analysis, but it's probably in the same vein, it's Off-Road Advisor. Off-Road Advisor is typically from Intel toolchain, tool suite, let's say, of HPC profilers. And the value of Off-Road Advisor is to basically help you to evaluate the portion of your code you can expect to be offloaded. So again, there is a strong assumption behind this, because it's based on hypothetical machines. So there is this ongoing discussion on integrated discrete systems for accelerated CPU, GPU, etc. But at least you have a baseline. You have something to explore and to refine. And Offload Advisor will help you to describe this upcoming system and understand in your application which portion of your code is expected to be offloaded and the potential gain you may expect. So it's also a refinement of this roofline-based methodology, but in that case, it's an opportunity to address accelerated computing. At scale, because it's a topic of major importance, in my opinion, discussing benchmarks, you need to also address what is going on at scale and not only mini-app. What you may consider is really not, okay, the compute phase will probably scale. I mean, it's the easiest thing to do to scale. You may have some imbalance, you may have some side effects, but you can expect to scale. What is really interesting is the rest. I mean, communication, initialization, I/O, etc. So here you have some sort of high-level cartoon of different methodologies. Some of them are event-based. I will comment on them later, SymGrid and SST. Some of them are based on traces. One of the limitations of traces is obviously you need to collect those traces. So if you want to simulate something on up to 100,000 MPI ranks, you need to collect first, and after you can basically project this volume of communication on the different topology. So it's a challenge. You need to have the machine available, you need to have the storage available for this, but okay, it's working well, and in terms of what-if analysis, it's a nice approach. For event-based approaches, like frameworks like SymGrid of SST, they have their own, impact from an application perspective. SST is really dedicated to a low-level mechanism at the networking level, with many different opportunities to tune the parameters of the switches, the congestion, etc. So it's really important if you want to design, a distributed system. One other aspect that is really important in my opinion is how to handle a real application between the compute and the communication phases. And in that case, it's one of the limitations of SST. I will comment on this later on. And SymGrid, that is a framework from my colleagues from Innovia, is let's say well balanced in terms of support of compute, networking, etc. But with some limitation in terms of the framework itself. I mean, the way you can really use it and the way you can scale for real application. So a few results and few, let's say, high-level things. So this is just an example from aggregated communications. So using some well-known benchmarks like SASOL, FISPEC, OpenGadget, and GROMAC. So it's just a way to evaluate the impact of the bisection bandwidth here in yellow. So if you can generate some, let's say, some results better than the bisection bandwidth, that means that you are not limited by this. And the thing you want to explore in that case is the so-called pod or supernode. I don't know how to describe this, but the first level of aggregation at the topology level. I mean, how this is impacting your application and how this may speed up or not your code. Back on SST, I will not go into all the details. One of the most important things is, I think, considering those frameworks, it's important to collaborate with large open communities, and it's the case with SST based on efforts from Sandia. One of the most exciting features of SST is the scalability. I mean, you can start analysis on very large configuration because the framework is parallel, and it's really convenient. One of the major limitations is that, indeed, if you want to build or to model a complex HPC application, it's based on motif, on pattern. So you need to redesign your application almost from scratch using pre-existing pattern. I mean, so it's not really convenient for a complex apps, but it may give you some insight on what to expect. Here, just an example from my colleague Sai, from the modeling of the HyperX topology for the level 2 and intranode is fully connected, and the evaluation, it's just the evaluation of various, let's say, configuration based on this two-level framework, two-level network, sorry. And here, the example of Halo two-dimensional, and on this graph, you can see in orange the bar for a 1D topology, and the other bars are representative of a 2D topology. So you can see in that case that the speed up coming from a more advanced topology can be easily simulated in that case. And obviously, Halo two-dimensional or three-dimensional, they are basic component or PDE-based applications. I won't go into all the details of SimGrid. I think one of the most interesting features is basically to rely on unmodified applications, so you can consider your application off the shelf, recompile using obviously a couple of well-documented, let's say, parameters, and run your original code, but with different type of topologies, different types of values for your networking, etc. And it's the case here with two quite different applications. The first one is LAMPS, mentioned previously as a reference app. So it's just a naive sweep to evaluate impact of latency or bandwidth for LAMPS. I should represent the topology associated with that, but it's just a sweep, I mean, to say it works. In that case, you can easily provide a more advanced description of the topology and explore the impact for LAMPS. Same thing for HPCG, where you can basically recompile your favorite HPCG and explore the impact at scale. So some really interesting contributions last few years on this topic. So a modeling of the all-reduced algorithms at scale from people at RICAN, contribution on the HPL benchmark from Tom Cornebees, and from Ethos working on portals and BXI. As a conclusion, and sorry for being so long, I mean, it's a multi-scale problem, obviously, and just like many different multi-scale problems, it's all about trade-off. I mean, granularity is extremely different from instruction level to the cluster level. You can consider so many different strategies, merge tools, include UQ, etc. Back to the topic of this meeting, I think the benchmark suite is quite important, especially the input size, because usually people may forget that the benchmark is not a simple mini-app or a simple loop, but it's also a set of input use case, and it's probably one of the most important things to really explore the behavior of future platforms at various scales. I think it's all for me. If you have questions, thanks.
Any question for Fabrice?
I'm staying with it. It's a very naive question.
When I was a postdoc in Boulder, I went to the MCAR, MESA lab, for the one who knows Boulder, and you could see one of the first Cray computers. and you could actually sit on it. There was actually a bench on the computer, and it was one of the first storic systems. And I wanted to ask you if your software that allows you to actually play with the network configuration, do you have a proof that indeed it's much better? I mean, there may be even much better configuration now 4D or much more higher dimension than the Tori, but I wanted to know if your software is able to demonstrate that Cray was right in having historic system.
To be honest with you, I don't have the specific answer for this Cray configuration, but both SST and SymGrid, they are well known for the ability to explore a very diverse set of topology. That's probably one of the value of those frameworks. So, back to your question on let's say, if Cray was right, or it's also related to how this may impact future design for next exascale or post-exascale system. What's the best way to design those scale up and scale out strategies, and the cost also, because switches, NIC, etc. It's all about cost also. So I don't know if Cray was right, but we have the tools to explore this if needed.
Any other question for Fabrice? Okay, thank you also for bringing the topic with the input data you mentioned. Yeah, that's also something quite large, and also with the AI and so on. Thank you. Almost there. Finish the day. That was really interesting, and first of all I want to thank all of our speakers for really playing the game in presenting your point of view on benchmarking. That was really rich. So I can skip that. This is on the Aristot website, and this is the purpose of the day, actually why we are here. So it all started with ADAC 12, actually, ADAC 12 workshop in February. And we have the community discussing about benchmarking and co-design. Actually, there was among the community at ADAC 12, we have mostly, at that time, we have mostly system admin, more supercomputing centers, and all the application part was quite missing in the discussion we had at that time about benchmarking. But in this discussion, the idea is that indeed, how do you do benchmarking? How do you co-design for what I call a whatever scale machine? That can be an exascale machine, a petascale machine, that can be HPC, HPC plus. So who's in this benchmarking part, and what does it mean? How are you involved? So yeah, since the last call, the last talk, it's going to be fun. So yeah, basically who's doing benchmarking, I put briefly on the paper, you have application developers, the vendors, sysadmin, and software developers. You may have more families, more CATS families. And you have, for all these 4 CATS, you have actually different priorities. And since you have different priorities, you have 4 different definitions and 4 different usage. However, there is a common point in between all these CATS, is the science. Again, you extract a benchmark from a scientific use case, a real scientific use case. So the thing is that what you can have sometimes is you have the 4 CATS working on the same scientific application. It could be, as we see today, Diablo, for example. And they are all doing benchmarking using an extract of Diablo, but this is a parallel work. And this is really too bad, because we could actually benefit from each other's experience to do that. So the idea is to bring this benchmarking discussion is how do you improve the knowledge, the sharing between all these communities. So how do you go from the parallel CATS to the CATS working all together? Yeah, why are we discussing benchmarking again? So yeah, indeed, it's like my grandmother, she's telling 1,000 times the same story, but she didn't have an exascale computer. So we can discuss that again. There is another topic with exascale area. I think we are all faced to this AI workflow that has to be mixed with HPC, with data analytics, and I don't even address the quantum computing wave, though we can discuss that in the possible white paper we can have later. But this is a brand new, different area than what we used to do 10, 15 years later in HPC. And at the end, when you see all this exascale area, we all have been faced to extensive benchmarking work at different levels. So the general idea of today is, this is something I propose, is to start a white paper altogether. So I wrote these slides before the talk, so I had in mind, let's say, a skeleton for the white paper. Since you gave a lot of idea, I have no clue how we will. We have to rework the skeleton. But yeah, the general idea is, let's bring the four cats around the white paper and provide some insights that could be guidelines on how this benchmarking thing is useful to everyone. So I can skip the original skeleton, let's say. Just quickly here, something that came into my mind, because that was thanks to ADAC 12 workshop again. There is maybe a minimum requirement list of metrics. Maybe it is not a list of metrics, maybe it is a family of metrics. It's a big spot of metrics we could define. And just make sure that depending on which cat you are, some metrics are more important than the others. So that could be viewed as a metadata. This list of metrics or family of metrics could be viewed as metadata of a benchmark. And the thing is, something that came from ADAC 12, at that time we discussed the fact that benchmark is alive because it is extracted from science that is itself alive, and anyway our architecture are alive too. So we also have to accept, and it was emphasized by your talk, we also have to accept that sometimes you have to erase and restart. So depending on who's using the benchmark, the priority of the metric is different. It doesn't mean the metric itself is not important at all and you have to ignore it, but just the priority you give to it is different. So maybe the sysadmin highest priority is energy to solution, actually that could be energy consumption. The vendor cat could be time to solution, the scientific cat could be numerical accuracy, or what I call scientific trustworthy. And for this metric, it would be, again, more, is your test case still alive in the application? So there is different usage, different cats, and there is probably a common spot to identify in this area, in this community, in this old usage we saw, the point of views we had today. And as an example, indeed, a benchmark is wrong when you miss one of the metrics. If I take, for example, the sysadmin cat and the vendor cat working together on a test case, but they forget the scientific trustworthiness of the benchmark, then the benchmark is wrong, because you're working on something that is not alive anymore, that will never run on the machine. On the opposite, the scientific cat should get in touch, for example, with the vendors to make sure that for the next 5 years, 10 years, it's still running with the next compiler, the next platform, etc. So that's why you go wrong. That was the illustration of the previous case. So that's why you are here today. That's because of ADAC 12. It's all because of ADAC. And the idea was to bring the community today to discuss really all the definition we have, the usage and so on. So eventually we can discuss the metrics definition, it can be something more high level. So I'm almost done. All of you are more than welcome to contribute to a possible white paper that would give insight, best practices about benchmarking. Anyone who would like to contribute is more than welcome. Maybe we will have to discuss, because again, I had something in mind before this talk today, and it was very rich, so we need to rework on that. Maybe more something about the philosophy, because I don't think we could find one definition that could fit all the cases. It's not the purpose, and we saw that today it's not possible. I put a warning, though. This idea was came from my brain in Japan with jet lag late in the night. So possibly this is a bad idea, but I found someone who would be responsible of it. This Jack. So you will receive the invitation to contribute to the white paper, and you will have to exchange all together. And with this, again, I'd like to thank all of our speakers, all of the participants. Thank you for coming. I'm really happy we have so much people. We're done for today. See you in about an hour, 6:45 in front of the hotel, and we'll go to the dinner place. Thank you, everyone.